Hello everyone. So we will be starting a new chapter today. The chapter name is actually virtual work method. It is also known as unit load method or Castigliano's second theorem. Okay, so whenever question asks in your semester to solve a particular question from a unit load method or virtual work method or Castigliano second theorem, then it all means the same. You have to carry out the same process. So actually, so we will be calling it as unit load method. Okay, unit load method. So it is actually a extended form of strain energy method. What is this strain energy method means? You must have studied in SOM. The strain energy method particularly deals with when suppose a particular beam is there and it is subjected to a particular load, then the beam gets deformed by a certain amount and a internal energy is stored in this beam. We use this internal energy to find the amount of displacement that has happened in the beam and the slope which takes place at the support. So how do we deal with that? Let's see. So first of all, the basic definition. What is the amount of energy stored in a body? You have studied earlier in your lower classes that the energy is stored in a body is the amount of work done on that. Okay, so if U is the internal energy of a body and W is the amount of work done, then U equal to W means the energy stored in the body will be equal to the amount of work done on that. Okay, and what is the formula of work done? Actually, work done is simple force into displacement. From the basic classes we have studied earlier, suppose a body is placed over here, we apply a certain force amount F and the body gets displaced from its original position to this position and the amount is X, then the work done is equal to amount of force multiplied by the distance moved by the body. This is the amount of work done. And what is the stored energy stored in this body? Energy stored will be equal to W into W equal to F into X. Okay, so how is it useful in a structural analysis? Suppose we will have a beam, force is applied over here and it gets deformed. Suppose the load applied is P and the deflection is Y, then what is the amount of work done on this beam? Amount of work done is force into displacement. What is the force applied here? Force applied is P and the displacement is Y. So this amount of work is done on the body. So what is the energy stored in this beam? Energy stored will be P into Y. So if we know the value of this stored energy and we know the value of this load P, then Y can be calculated easily as U by P, internal energy by load applied. Okay, so this is the value of deflection that is going to be happened in this beam. In this way we use energy methods or strain energy methods to calculate the displacements in a beam. So before we move further, we sorry, I need to get you acquainted with some of the terms, like displacement. What is displacement mean in structural analysis? Displacement may be of two types. Okay, first is actually a linear displacement maybe, and the second one may be a rotational displacement. The rotational displacement is also called as slope. The linear displacement is denoted by this delta, or maybe sometimes y, or sometimes del, and the slope is represented by theta. So what does this linear displacement, this rotational displacement means actually? So if suppose we have a beam, this is simply supported beam. Okay, a load is applied over here, then when the load is applied, p amount of load is applied, then what should be the deflected form of this beam? Okay, so the deflected form of the beam will be like this. Beam will deflect like this. Okay, so suppose we have a displacement y here, then so this y is actually a linear displacement. So here it is a linear displacement, and if we look at the supports, then if we draw a tangent from here to here, then we see that the originally beam was like this and it gets deflected towards like this, then this is the amount of angle by which it gets deflected, so it is angle theta. So these are the two displacements that we deal with in our structural analysis. Okay, so what the displacement means actually? So if we apply a force, then force causes linear displacement. Causes linear displacement or delta, and if we apply a moment, then it causes slope. Okay, so remember this thing, these two things, that force causes linear displacement and the moment applied causes a rotational displacement. Okay, so let's move towards the energy methods. So we from basic strength of materials, we know that energy stored in a body is equal to m square dx upon 2ei integration, where m is the moment at any point on the beam, e is the Young modulus of the member, and I is the inertia of the member. So u is equal to w. This is the equation for strain energy equation. If we go on deriving this value, then we will obtain the expression for unit load method or virtual work method. So the expression for virtual work method or unit load method is u equal to capital M into small m by ei into dx. Okay, this is the equation for unit load method. What is the value of m? M is actually moment expression due to actual loads, and small m is the moment due to virtual load. What is this actual load and what is this virtual load? We will explain further. Okay, so let's carry out with an example. Suppose we get to see a cantilever beam like this. A certain amount of load is acting over here, P. So at any point x, the capital M will be P into x. This is minus sign because the deflection of this beam will be hogging 1. Okay, so this is the capital M, which is the moment due to the actual load on the beam. What is the small m? We remove all the loads that are acting on the beam, actually acting on the beam, and we just apply a virtual unit load. This 1 kilonewton is actually a virtual unit load. What is this meant by this virtual unit load? Virtual unit load is actually the load which was not actually acting on the beam. We just introduced it in the beam so that our calculation will be get easier. So this 1 kilonewton we apply on the beam and then calculate the value of a small m and then carry out the process further. Okay, so now I hope that you get the value of what is m and what is capital M. Capital M, what is a small m. So just write down capital M is actually the moment expression due to actual load. Okay, and what is the value of small m? It is actually moment due to virtual unit load. Okay, so this is capital M, this is small m. How now if we move further, then we know that strain energy is equal to work done. So if in that beam the beam gets deflected by an amount of delta, then what is the work done? Work done is force into displacement. What is the force over here? Force is P and displacement is delta. So this is the work done, and U is equal to W, and we also know that U equal to mm dx by EI. So finally U equal to W. This gives us P into delta equal to mm dx by EI. If we apply a virtual unit load, then the value of this P is actually 1 kilonewton. So we obtain the value of delta as mm dx by EI. So this is the expression that we have to remember. The value displacement is equal to capital M into small m into dx by EI. Okay, similarly if we are going to deal with the slope, what is the value of slope? So it will be a similar one as that of displacement, mm dx by EI. But how we are going to use these two equations? These two equations are important for this chapter. Okay, and how we are going to use it, we will see with an example. Okay, so just remember one thing, that whenever we are going to find deflection, we are going to apply unit load, and whenever we are going to find the slope, we will apply unit moment. Why? Because we know that force causes linear displacement and moment causes slope. So in case we have to find slope, we will apply unit moment, and in case we have to find deflection, we will apply unit load or unit force. Okay, so let's proceed with an example. Suppose a cantilever beam is given to us. This is the beam, and a load is given over here. The value of this load is 10 kilonewton. This is A, and this point is B, and the distance is 5 meter. Okay, so the question asks, actually the questions ask, find deflection of the free end B and what is the rotation at the free end B. So if this beam gets deflected, like this, okay, so at the free end we have to find this amount of value, and at the free end it must make some angle, so we have to find this angle. Okay, so let's proceed. First of all, we will find what is the value of deflection at B. Okay, so we have one basic formula. What? Deflection equal to capital M into small m into dx by EI. We will use this equation or this formula in finding deflection at B. So how to use it? If we draw the diagram over here, this is the original beam. Load was acting 10 kilonewton, point B, and this is point A, and this is 5 meters. Okay, we know deflection is capital M small m into dx by EI. So what is the M? M is actually this capital M. M is actually moment due to actual load. So this is the actual load, which is 10 kilonewton. What is the moment at any point X on the beam? At any point X, what is the moment acting over here? It is 10 into X with a negative sign. Why negative sign? Because the deflection is hogging. So value of M is minus 10x. Okay, what is the value of this small m? Suppose we have a beam. To find this small m, we remove all the loads acting on the beam. Okay, so this is the beam that we get after removing the loads of 10 kilonewton. This is 5 meter, and apply what we have to find. We have to find deflection. So we will apply 1 kilonewton of load. Where do we apply this 1 kilonewton of load? At the point where we have to find the deflection. We have to find deflection at B. So we will apply this 1 kilonewton load at point B. And then we will find the value of this small m. Okay, so after applying this 1 kilonewton at point B, what is the value of small m? At in point X, it is minus x. Okay, this is the value of small m, and this is the value of capital M that we have obtained. Okay, and what is the limit of this integration? It will be from 0 to, what is the length of the beam? 5 meters. So it will be from 0 to 5 meters. Okay, so let's proceed with it was actually deflection at B is equals to m dx by EI 0 to 5. So put the value of m. It was actually minus 10x. What was the value of small m? It was actually minus x dx by EI 0 to 5. Then the equation gets minus minus plus 10x square dx by EI 0 to 5. After proceeding this integration, we will obtain the value as deflection at B is equal to 1250 by EI. Okay, how? Let's solve it in detail. Okay, we had this equation as 10x square zero to 5. So we removing this 10 by EI outside the integration, we are left with x square dx. So this is 10 by EI x cube by 3. The upper limit was 5, lower limit was 0. So after solving this, we will get 10 by EI into 10 by 3 EI to 125. So the value comes out to be 1250 by 3 EI. Okay, this is the value of deflection obtained. Means this was a cantilever beam. This was the cantilever beam where the 10 kN load was acting. It gets deflected by this, so this amount is 1250 by 3 EI. This is the value of deflection we have obtained. Okay, I think it is clear. So let's move to the second part. What the second part asks? Second part asks what is the slope at B. So here we have to find the slope. So proceeding in the same way, we had this cantilever beam. The load was acting over here, 10 kN load. This was 5 meters. So what we had slope as dx by EI. Okay, so what's the value of this m? Capital M was the moment due to actual load, and this small m was moment due to the virtual unit load. So now here we are interested to find the slope, so we will apply a virtual moment here. In the last case we had applied virtual unit load over here, but in this case we have to find slope. So slope occurs due to moment, so we will apply 1 kilonewton meter of moment over here, and then we will find the value of small m. So what is the value of small m? It is actually minus 1 kilonewton. Why minus? Because the beam is deflecting towards this side, towards hogging. Okay, this hogging is occurring, so the moment will be a negative one. And what is the value of this capital M? It is actually 10 into x. At any point x, it is also negative, minus 10 into x. So we have find the value of small m, we have find the value of capital M. Let's proceed and obtain the value of theta. So theta is actually dx by EI 0 to 5. This m was minus 10x and this small m was minus 1 into dx by EI 0 to 5. So the expression is 10x dx by EI. It is 0 to 5. So we will obtain theta B as 10 by EI into x dx 0 to 5. Sorry, it's creating a problem. 0 to 5. So we get 10 by EI x square by 2 0 to 5. So we get 10 by 2 EI into 25. Okay, so the theta becomes out to be 250 by 2 EI or 125 by EI. So we have obtained the value of deflection at B, and we have obtained the value of slope at B by using unit load method. So what we did, actually, let us revise. We had to find deflection at this free end B where 10 kilonewton load was acting. Okay, so what we did, deflection, we know that formula mm dx by EI. We integrated from 0 to 5. Why? Because the length of this member is 5 meters. Okay, so we get from 0 to 5 meters. We calculated this value of m. This m was actually moment due to the actual load. Actual load was 10 kilonewton. So this 10 kilonewton was imposing at any point x. This 10 kilonewton was imposing a moment of 10 into x. It was negative because the beam was hogging. So the capital M was 10 minus 10x. What is the value of a small x? Small m. Small m was, how did we derive this value of a small m? We had this beam, and we removed all the loads that were actually acting on the beam, and we just applied 1 kilonewton load at the point where deflection was to be determined. We had to determine the deflection at point B, so we applied the unit load at point B, and now we found the expression at any point x. So small m was minus x. So we just put the value of m and this small m over here and over here, and we integrated, and we obtained the value of this delta B. Okay, but in the next scenario, what we had to find, we have to find deflection at B. So what we did, it was actually capital M small m dx by EI. We had this capital M, which was the moment due to the actual load. Actual load was 10 kilonewton. So the moment acting here was 10 into x. So this we had find 10x with negative sign. And what was the small m? Small m was the, we had to find this theta. So what we did, actually, we just removed all the loads, and we had to find this theta. So we applied a unit moment, and then we found that at this point the moment, what is the value of this moment at any point on the beam over here? This is actually a constant moment that is applied over the beam, so it is actually an original moment, so it need not to be multiplied with the distance. Okay, because moment is actually force into distance, but this is not a force, this is actually a full moment which is applied at the free end. So throughout the beam, at every point, the value of this moment will be constant. So at any point on the beam, the moment will be 1 kilonewton, and it is actually negative because the moment applied is the beam is bending in a hogging position. Okay, so we put that value of capital M over here, and we put the value of a small m, and we derived the value of theta B. Okay, so in this manner we find the slope and deflection using unit load method. Okay, let's proceed further with an example number 2. If we have a simply supported beam and a point load is acting P over here, so what will this point A, this point is B, and this point is C. So what is the value of this beam will bend in which manner? This beam will bend along this manner. So at point C, deflection. So what is the value of deflection at point C? We have to determine this deflection at C using unit load method. So let's solve this question. So first of all, what we will do, we will determine the value of reactions. Okay, so it was a simply supported beam like this. Okay, so it is actually a symmetric beam. So what will be the reactions? Reaction will be equal P by 2, and here it will be P by 2. Okay, we have this point is C, and this point was A, this point was B. So we know that deflection at C is equal to capital M small m by EI into dx. So we will determine the value of this capital M and this small m. So if we get to find the value of this capital M, this will be a moment due to at any point x. Suppose this is point x. So it is the moment due to the loads at any point x. So what is this value of M? It is actually this P by 2 is acting over here. So this P by 2 into x. P by 2 into x. This is the value of capital M. And now what is the value of this small m? To determine the value of this small m, we will remove all the loads acting on the beam and apply a unit load. Where? So this was the original beam. We just removed all the loads. Here it was point A, it was point B, and the midpoint was point C. We removed all the loads and we had to determine deflection at C. So we will apply at 1 kilonewton at C is applied. Okay, so let's apply 1 kilonewton at point C. This is 1 kilonewton load. So due to this 1 kilonewton load, 1 by 2 kilonewton of reaction will be generated here, and 1 by 2 kilonewton of reaction will be generated here. Now we will find small m. Small m is actually the moment at any point x. So what is the moment at any point x? Here it will be 1 by 2 into x. So we have derived the value of capital M as P by 2 into x, and this is the value of small m, it is 1 by 2 into x. So we will put the value in equation 1 and we will derive delta mm dx by EI integration from 0 to L, total length of the beam. So let's put the values, and after putting the values we will obtain deflection at C is equal to P by 2 into x into 1 by 2 into x dx by EI from 0 to L. But now here we see that the beam is a symmetric beam. Symmetric beam means the portion along the left hand side and along the right hand side is same. Okay, so this is actually a symmetric beam, so we will carry on the integration by considering it like this. It will be 2 into the same expression, p by 2 into x by 2 dx by ei 0 to limit will be L by 2. Okay, because it was symmetric beam, so we just the left hand side and right hand side will be equal, so we will multiply it by 2. Okay, this 2 we have multiplied over here, and the integration is carried out within limits from 0 to half of the length of the beam. Okay, this is half of the length of the beam. So if we carry on the integration like this, okay, let's carry out the integration. It will be actually deflection will be px by 2 into x by 2 dx by ei 2 into 0 to L by 2. So it will be p x square by 4 ei dx 0 से L by 2. So let's remove all the constant terms outside. So it will be px square by 2 ei into x square dx, sorry, x square dx 0 to L by 2. X square will not be present here. Okay, so here we will get p by 2 ei into x cube by 3 0 to L by 2. It is p by 2 ei into 1 by 3 into this x cube means L cube by 8. So the equations comes out to be pl cube by 3 to the 6, 6 is 48 ei. So okay, this will be the value of deflection at point C. So the deflection at point C obtained is pl cube by 48 ei. Okay, this is correct. Okay, so we see that how to carry out deflection. We saw two examples based on unit load method. So the question comes in various varieties, so I request you to please go on and solve different kinds of questions to make your concepts more clear about this unit load method. Okay, so if you have to solve a question, then solve this question. This is a cantilever beam. A 10 kilonewton load is acting over here, and a 10 kilonewton load is acting over here. This is 5 meters and this is 5 meters. Okay, this is point A, this is point B, this is point C. Okay, find deflection at point C. Okay, find deflection at point C and find rotation at point C. Okay, at the free end. You can solve this question. Consider the inner I as constant throughout the section. So I can suggest you few books to solve. I have sent the PDF of SS Bhavi Katti. Okay, you can solve all the examples. all the examples of only beams. Okay, I have taught you only beam questions, so you can just try some examples of only beams. Just leave out the frames. Frames will be structure like this. This I will teach you in the next session. Okay, then we will see how to calculate slope and deflection. This will deflect in this manner. Okay, so in the next session I will teach you how to find slopes and how to find deflections in frames using this unit load method. Okay, so that's all for now. Okay, thanks.